Welcome to the course PH8253 Physics for Electronics Engineering. We are dealing with magnetic and dielectric properties of materials, Unit 3. In today's class, we will be discussing the types of magnetic material. Previous class, we have seen that susceptibility chi equal to mu r minus 1. The mu r is relative permeability and chi denotes susceptibility. Depending on the values of mu r and chi, material can be classified into three types. Mu r less than 1, chi has a slightly negative value, mu r slightly greater than 1, and chi has a small positive value, whereas mu r and chi are large and positive. These are the three possibilities. And the corresponding materials for these conditions are diamagnetic, paramagnetic, and ferromagnetic. So this is the broad classification of materials based on their magnetic property. So these are types of magnetic material or types of magnetism. As can be seen from the values of relative permeability mu r and susceptibility chi, both dia and para magnetism are weak forms of magnetism. Whereas ferromagnetism is strong. Let us now analyze the various characteristics of diamagnetic material. Diamagnetic material. As we have seen in diamagnetic material, chi has a small negative value, whereas mu r is less than 1. Examples for diamagnetic material include gold, germanium, silicon. Diamagnetism is a weak form of magnetism and it is observed only in the absence of other forms of magnetism. Since it is very weak and is evident only when other magnetic properties are absent, it is of no practical use. But diamagnetism is intrinsic to the material. It can be observed only when the external field is present. It is present only when the external field is applied. It is a non-permanent, that is when the external field is removed, the diamagnetism disappears. So it is a non-permanent. In place between electromagnets, diamagnetic material move to weaker regions of the field. This is because of the fact that in the presence of magnetic field, a small magnetic moment is induced in the direction opposite to that of the field. With no applied field, the magnetic dipole moment is zero in case of diamagnetic material. Whereas when a external field is applied, the field H field, the external field is applied in this direction, dipoles are induced and aligned opposite to the direction of the field. And the dipole moment induced is small. The dipoles are aligned in the direction opposite to the applied field. So this can be visualized as the orbital and spin magnetic moments are such that their vector sum is equal to zero. So hence there are no dipoles present in the absence of external field. Whereas when an external field is applied, dipoles are induced. They are induced such that their alignment is opposite to the applied field. Since it is a weak form of magnetism, it is of no practical importance, but it is intrinsic to the diamagnetic material. That is, because of the electronic arrangement, uh, the diamagnetic property is intrinsic to the material. Let us now discuss about paramagnetic material. As we have seen, a paramagnetic material is one in which relative permeability is slightly greater than unity, and chi is a small positive value. Susceptibility has a small positive value. So, in the absence of external field in a paramagnetic material, there are dipoles present, but the dipoles are aligned such that the net magnetization is zero. So the dipoles are randomly oriented in the absence of the external field, such that net magnetization is zero when the external applied field is zero. But when an external field is applied in this direction, the dipoles get oriented along the field direction. The dipoles are randomly oriented in the absence of external field. In the absence of external field, the orientation of the magnetic moments are random and hence the net magnetization is zero. Whereas when an external field is applied, the dipoles are preferentially oriented in the field direction. When an external field is applied, the dipoles are preferentially oriented in the field direction. So examples of paramagnetic material include include aluminium, air, magnesium, platinum, Fe2O3. The presence of dipoles, even in the absence of external field, can be attributed to the fact that the spin and orbital magnetic moments together have non-zero value of dipole moment. Paramagnetism is again a weak form of magnetism. The third type of magnetic material is ferromagnetic material. We have both mu r and chi are large and positive. Large positive magnetism observed in materials such as iron, nickel, cobalt, gadolinium can be explained on the basis of the domain theory of ferromagnetism. So this is a permanent form of magnetism, and hence ferromagnetic material are used in a lot of applications such as permanent magnets, electromagnets, transformer cores, and so on. Permanent magnetization is observed in case of ferromagnetic material. We will discuss the domain theory of ferromagnetism in the next class. Thank you for now.